Now let's compare the impact safety between two HMX-based PBX with different binders. PBX is polymer bonded explosive and plastic bonded explosive. Binders play an important role in the safety of plastic bonding explosive. For the performance improvement of HM-based explosives, the impact safety for the explosive using thermoplastic polyurethane as binder was investigated by comparing with the use of fluorine rubber by experiment performed with a self-designed impact test device to measure critical ignition velocity. It was found that the critical ignition velocity, which is 277.36 mass per second of stain 5703 containing explosive, was 9.3% higher than that of F2604 containing explosive. By analyzing the particle size distribution and morphological characteristics of the impacted powder, it could also be inferred that stain 5703 binder has better bond behavior than F2604. Now, experimental material and parameters. The experimental parameters are the raw HMX, which has density 1.902 gram per centimeter cube and size 100 micrometer with the detonation velocity of 8917 mass per centimeter, was purchased from Gansu Yincheng Chemical Company. The F2604 1.82 gram per centimeter cube was provided by the Shanghai 3F New Material Co Limited Stain 5703, which has density of 1.2 gram per centimeter cube, was obtained from Novin Chemical. The raw PBX, which is plastic bonded explosives powder, was prepared by the two-step solvent evaporation method. Firstly, the raw HMX was coated by the insensitive system. Subsequently, samples can be formed by applying binders to bond aluminum and other components to the surface of the insensitive explosive. Finally, a charge was made in model under 5 MPa pressure. The detailed preparation process of the charges. Advanced, safer formulation of HMX are existing work on phlegmatization and co-crystals highlights progress. Yes, systematic studies optimizing binder systems, nanostructures, composites, or novel energetic co-crystals with both high performance and low sensitivity are limited. Classic formulation often face trade-off that requires deeper investigation. Now let's talk about the application of HMX. Owing to its exceptional detonation performance, high thermal stability, and favorable energetic density, HMX has found extensive application in advanced military and aerospace energetic system. Some of other applications are: the first application of HMX is polymer bonded HMX derivatives. HMX is commonly used in melt cast explosive when blended with TNT. Such formulations are collectively known as octols. In addition, polymer bonded explosive, which is PBX compositions based on HMX, are widely employed in the production of missile warhead and armor piercer shaped chargers. Applications of HMX in oil and gas perforations. HMX is also used in the process of perforating the steel casting in oil and gas wells. The HMX as is built into a shaped charge that is denoted within the well bore to punch a hole through the steel casing and surrounding cement out into the hydrocarbon bearing formations. The pathway that is created allowing formation fluid to flow into the wellbore and onward to the surface. HMX in asteroid sampling missions. The Hayabusa 2 space probe used in HMX to evacuate a hole in an asteroid in order to assess material that had not been exposed to the solar wind. Now let's talk about the simulation of printer nozzle for 3D printing TNT HMX based melt cast explosive. Fuse deposition modeling FDM as one of the additive manufacturing technologies has been widely used in various manufacturing industries to fabricate products with complex structures. However, the application of FDM in energetic materials EMS was still less common. In this work, the effect of high melting explosive solid content and particle size of the viscosity of molten TNT HMX explosive were investigated. Then the computational fluid dynamics CFD and discrete element method DEM were used to simulate the influence of viscosity, pressure, temperature, nozzle diameter, and particles on the fluid flow inside the 3D printer nozzle. In addition, an FDM 3D printer was used to prepare TNT HMX based explosive and various characterization methods were applied to explore the structure and morphology of the printed samples. The sustainability and HMX challenges and green alternative. The first one is environmental and health impact. Toxicity. HMX is a suspected human carcinogen. It contaminates soil and groundwater at manufacturing and testing sites, posing long-term ecological risk. Life cycle analysis (LCA). The synthesis of HMX involves hazardous reagents like nitric acid and acetic anhydride and generate toxic waste including pink water from purification process. End of life disposal. Demilitarization of DMX containing mutination often involves open burning or detonation releasing toxic fume which can be oxides of nitrogens and HCN and particulates. Sustainable practices and research. Green synthesis. Research focuses on using ionic liquids or biocrystals to reduce water and energy consumption in HMX production. Bioremediations. Microorganisms can degrade HMX in contaminated sites under anaerobic condition, breaking it into harmless products. Insensitive mutination. Formulating HMX with polymers PBX reduce accidental detonation risk, minimizing environmental release. Recycling. Recovery of HMX from obsolete mutinins for reuse in commercial explosive like mining through technically challenging. Future direction. Bio-inspired energetic material exploring non-toxic high nitrogen compounds like tratrazine derivatives as potential replacement. Life cycle assessment LCA implementing cradle to grave analysis to quantify and mitigate the environmental footprint of HMX based explosive. Now the other important topic which we will discuss is HMX for graphene doping. The interfacial interaction between HMX molecules and coating material is the key to the safety performance of explosives and has received extensive attention. However, screening suitable coating agent to enhance the interfacial effect to obtain high energy and low sensitivity explosive has been a major challenge. In this work, HMX, PEL, RGO, C3 and 4 HPRGC composites were innovatively prepared by multi-level coating strategy of two-dimensional graphite and GC3H C3N4. The GC3N4 used for desensitization has a rich pi conjugated system and shows outstanding ability in reducing frictional sensitivity. The hierarchical structure of HPRGC formed by electrostatic self-assembly and pi-pi stacking can effectively dissipate energy accumulation under heat and mechanical stimulations through structures evolution, thus exhibiting a prominent synergic desensitization effect on HMX. The result shows that RGOG C3 and 4 coating has no effect on the crystal structures and chemical structure of HMX. Preparation of Preparation of HMX GC3N4HC. GC3N4 was obtained by the conventional high temperature calcination method. 10 gram urea was calcined in a muffle furnace at 550 degrees Celsius for 3 hours. Heating rate was 3 degrees centigrade per minute, then cooled to room temperature, ground and dried for later use. The composite HC was prepared by the physical grinding method. 960 milligram HMX and 40 milligram GC3 and 4 were continuously ground with a mortar until the mixture was uniform and delicate to obtain HC composites. Preparation of HMX spell HP. The composite HP was prepared by water suspension method. 980 milligram HMX was uniformly dispersed in 50 ml deionized water by ultrasonic steps, and 10 ml PEL aqueous solution was injected into the HMX suspension at 25 degrees Celsius, stirring for 2 hours to obtain the blending state of HP. Preparation of HMX PEL RGO composites. The composite's HPRG was fabricated by in situ reduction methods as displayed in the figure. Specifically, 20 gram RGO and 400 micro L-hydrazine hydrate was rapidly added into the above solution with 3 hours of stirring in an oil bath at 100 degrees Celsius. The products precipitated at the bottom of the flask when the mixture was cooled at room temperature. Through filtration and washing steps, the filter cake was washed 3 times with deionized water and dried in a vacuum drying oven for 24 hours. And composite HPRG 1% was obtained as a pale black powder. Now the reason why are we using HMX for doping? HMX, which has molecular formula C4H8N8 and O8, is a nitrogen-rich molecule, 22.2% nitrogen biomass with a high density of nitro group. Upon controlled thermal decomposition or detonation, it releases reactive nitrogen species which can be nitrogen radical NO, NO2 and CN fragments, carbon cluster and hydrocarbons, and the other last thing is high energy transient condition which is high temperature and pressure. These products can in theory functionalize or dope graphene by introducing nitrogen atoms into the lattice or creating defects sites. Effects of graphene silane metal nanocomposite on the combustion performance of HMX-CMDB propellant. A series of novel graphene silane metal nanocomposites with different active metals and molecular structures were designed, synthesized, and characterized using SEM, EDS, FTIR, XPS, and Raman instruments. Effect of the as synthesized graphene silane metals nanocomposites on the combustion performance and mechanism of HMX CMDB propellant were studied. Among the nanocomposite considered like S792, nickel has the best effect on the combustion performance of HMX-CMDB propellant, which makes the propellant possess high burning rate, low pressure index, and good combustion stability. The excellent combustion performance of HMX-CMDB propellant containing S790 nickel is closely related to the formation of filamentous clusters, the decrease of dark zone thickness, and the increase of gas phase temperature gradient. In addition, the formation of a flocculent network carbon skeleton and the decrease of metal aggregations in the quenched sample also contribute to the improvement of the combustion performance. Effect of graphene on ignition mechanism of HMX powder and propellant under low velocity impact. In order to investigate the effect of graphene powder on the ignition mechanism of cyclotetramethylene, tetranitramine, HMX, and propellant under low velocity impact, an improved drop hammer impact system equipped with a high speed camera was used to study the ignition response of HMX. HMX and graphene mixture and graphene based propellant. The result shows that HMX undergoes mechanical deformation, physical melting, and chemical response under different impact loading heights. The mixture of HMX and graphene experience crack ignition, crack propagation, jetting, and carbonization effect during the whole impact loading process. The whole process of graphene-based propellant impact undergoes mechanical deformation and mechanical response, which is hotspot and ignition. The ignition threshold of HMX and HMX powder graphene mixture were 20 and 25 centimeter respectively. It is revealed that graphene powder has an inhibitory effect on the hot spot ignition formation of HMX. The ignition threshold of the graphene-based propellant is 4.245 mass per second. It is revealed that the ignition mechanism of the three types of specimen under low velocity impact loading is particle friction. Graphene microstructures engineering for propellant. As a special polymeric composite and military strategic material, composite solid propellant has attached extensive attention and efforts to improve its performance. Graphene being regarded as an ideal material to enhance the performance of propellant because of its excellent physical and chemical properties such as ultra strong strength, large specific surface area, remarkable thermal conductivity, and phenomenal electrical performance. Moreover, the microstructures engineering based on graphene has been demonstrated to reveal effective influence on the composites. Recently, many new advances have been developed in microstructure engineering of graphene for propellant-related applications. In this article, we first present an overview of the main synthesis method of the graphene. Subsequently, these new advances are reviewed, discussed, and summarized carefully. Now, the first method of synthesis are compatibility of graphene-based scatters with the energetic ingredients. To demonstrate the discrepancies of the International Standard on Compatibility Evaluation for Energetic Additives, a comparative study on compatibility of three typical graphene-based catalysts with common energetic ingredients has been done by using DSC and VST methods. Based on some unusual findings, further suggestions are proposed on improvement in the compatibility evolution standards. The compatibility results from the DSC and VSC methods are high melting explosive GT nickel, high melting explosive GC copper, APGC copper, APGT nickel, and RDXGC copper systems are contradictory. The major description between DSC and VSC results are caused by the combination of contradictory nature of the stabilization and crystal and catalytic effect of these additives on the corresponding energetic ingredients. It has been shown that the HMX GC nickel, HMX GT nickel, APGT nickel, GC NI, and all the other factors which we have written there are mixture have demonstrated moderate compatibility. In general, the copper-based additives, even under the stabilization of graphene oxides, are not so compatible with nitramine oxidizers and AP. These results indicates that each of the evaluation standards on compatibility has its own features and limitation. The DSC standard is probability not suitable for the evaluation of compatibility of GC nickel, GC copper, GT nickel, GT copper, and GA copper with energetic ingredients. The compatibility assessment cannot simply rely on the available standards, and more comprehensive evaluation procedures needed to be established according to the nature of the material evaluated. Now, the techniques for the graphene doping are proposed techniques and mechanism. First of all, let's talk about the preparation of graphene. Graphene was first produced by the mechanical exfoliation of graphite in 2004. 32. This method can be obtained the monolayer or few layer graphene with perfect structures. However, it is expensive and has very low efficiency. Over the past 10 years, with the continuous efforts and exploration of researchers, numerous novel methods have been put forward to synthesize graphene. First of all, combustion or detonation assisted doping. The process of combustion assisted doping is mix HMX with graphene precursors. The graphene precursor can be graphene oxides and reduced graphene oxides or preformed graphene. Ignite or thermally decompose HMX in a controlled environment. The controlled environment can be sealed reactor or inert atmosphere. Use the released energy and nitrogen species to drive doping reaction. Now, the mechanism of combustion assisted doping is at 280 to 300 degrees Celsius. HMX decomposes via N to NO2 bond cleavage, generating NO2 radicals. These radicals and secondary species like NO, N2 can react with the graphene sp2 carbon lattice, substituting carbon atoms or forming pyloric, pyridinic N motifs. The shock waves or rapid gas expansion from decomposition may create lattices defects, facilitating dopant incorporation. Reporting the example of this type in the patent methods, HMX graphene oxide composites were shock compressed to produce nitrogen doped graphene for supercapacitors. The detonation wave provided simulation reduction of GO and N doping. Chemical vapor deposition using HMX as a precursor. Sublimate or vaporize HMX in a CVD furnace. Decompose HMX on a metal crystal and co-deposit carbon and nitrogen from HMX pyrolysis onto a substrate. Mechanism. HMX vapor decomposes on the hot substrate, releasing carbon, hydrogen, nitrogen, oxygen species. Nitrogen incorporation occur either in situ during graphene growth on the catalytic substrate, post-growth doping, pre-mixture, pre-existing graphene via surface reactions. The advantages of this type of doping is HMX provide both carbon and nitrogen in a single molecule, potentially simplifying nitrogen-doped graphene synthesis. But the challenge is controlling the nitrogen-carbon ratio and avoiding excessive defects due to oxygen content. The third point is solid-state thermal annealing of HMX graphene mixture. Mechanically mix HMX powder with graphene or graphene oxide, seal in an ampoule under vacuum or inert gas. Heat gradually to allow HMX decomposition and doping without explosion. The mechanism of this type is slow pyrolysis of HMX release nitrogenous gases that diffuses into graphene layers. Nitrogen atoms incorporate at vacancy sites or edges. The possible reactions of this is HMX reacts with the graphene, which results in the formation of N-doped graphene, water, carbon monoxide, carbon dioxide, and nitrogen as a side product. The safety precaution for this type of reaction is this requires strict temperature control to prevent deflagration. Laser plasma induced doping using HMX as nitrogen source. The process is coat graphene with a thin layer of HMX via solution casting. Irradiate with laser pulsed NdYAG or plasma. HMX decompose locally, releasing nitrogen that dopes the underlying graphene. The mechanism of this reaction is photothermal or plasma energy breaks HMX bond, creating reactive N species that bond to graphene lattice defects generating by irradiation. In successful, the resulting material should show SPX peaks at 398 to 401 electron volt. Raman shift increase D band intensity. which is defects from doping maintain 2D-G ratio, enhanced electrical conductivity, and type doping if an incorporated and elemental mapping DES or SEM showing and distribution. HMX powder and propellant. In order to investigate, like we already discussed, HMX powder can be used as a propellant in case of aerospace materials. Integration with propulsion system. Although HMX has been studied in propellant blends, its role in modern rocket propulsion systems, especially in sustainable or hybrid propulsion contexts, is not yet a mature research area. This is scope for research on the combustion dynamics with metal additives and modeling of thermal stability under operational cycle. Recent research has expanded graphene doping strategies into novel, multi-modal, and application-specific area. The other key factors for doping which will be discussed are as follows: multi-modal and co-doping strategies. Moving beyond single element doping to synergetic multi-element system. The examples for this type is nitrogen sulfur co-doping creates asymmetric spin density enhancing oxygen reduction reaction ORR catalytic activity beyond platinum carbon benchmark in fuel cells. The sulfur atoms polarize adjacent carbon nitrogen bond creating superior active sites. Boron nitrogen pair doping. Boron and nitrogen atoms substituted at specific relative position meta position creates unique electronic structures for quantum emission and spin photon sources. The strain engineered doping. Applying mechanical strain to graphene alter its electronic structures. Combined with doping, this creates tunable pseudomagnetic fields and variable band gaps. Strain plus N doping, which is uniaxial strain on N doped graphene, can modulate its work function by up to zero point 0.8 electron volt, enabling tunable graphene electrodes for flexible electronics. The other is patterned strain field created via substrate engineers, leading to spatially varying doping effectiveness and novel electron confinement. Machine learning accelerated dopant discovery. High throughput computational screening combined with ML model predicts optimal doping configuration. Research using Gaussian process regression to screen 2000 dual dopant configuration, identifying nitrogen mobidium co-doping so optimal for hydrogen evolution creation. HER catalysis later experimentally verified with a record low over potential of 32 MB. Sustainable and green doping precursors. Replacing toxic hazardous precursors like ammonia, borane with biomass or waste-derived alternatives. The examples are chitosan-derived nitrogen doping, pyrolyzed with graphene oxide, produced high-quality and doped graphene with 6.3 percentage of nitrogen, excellent for supercapacitors. The urine-based doping. Human urine rich source of urea and salt serve as an effective nitrogen source, achieving 4.18% doping as proof art concept for circular economy. On demand and reversible doping. Using external stimuli to modulate doping levels in real times. Electrostatic ionic liquids. Applying a gate voltage in an ionic liquid environmental can reversibly tune the doping types and concentration in graphene. Photodoping, UV radiations on graphene decorated via photoactive catalyst azobenzene creates transient N types doping. Doping for quantum technologies in this single electratom doped with a phosphorus creates stable addressable quantum bits with long cohesive times at room temperature. Doping in graphene analogies. Hexagonal boron nitramides doping introducing carbon atoms into HBN creates single photon emitters with higher superior stability. Twisted bilayer graphene. Doping in magic angle system dramatically alters correlated electron states, enabling control over superconductivity and Mott insulator pairs. In situ characterization and during doping. Environmental stem doping, observing dope incorporation in real time under reaction mechanism. The advantages and challenge. The advantages and challenge of graphene doping is single source of carbon nitrogen precursor, high nitrogen content, and it is also energy efficient HMX exothermic reaction. The challenges are safety because HMX is an carcinogenic material. Its control is not easy because it is not easy to transport byproducts. Oxygen from HMX may create unwanted oxides and so scalability not suitable for industrial scale. The stability sustainability challenge are using existing energetic materials and cones as synthesis and handling using environmental footprints using doping efficiency may be lower than conventional ammonia CVD methods. Future outlooks. The field is shifting from doping for conductivity to precision doping for functional engineer specific dopant arrangement to create quantum emitters, single atom catalysis, and or topological states. The integration of automated experimental with real-time characterization and ML feedback loops to poise to accelerate discovery of next generation dope graphene materials with tailored properties for energy, quantum, and quantized energetics. Conclusion. In conclusion, HMX stands as a powerful but environmentally challenging explosive, prompting research into greener synthesis and remediation. Simultaneously, graphene doping has evolved into sophisticated toolkit for energetic engineering advanced materials. Together they simplify the dual characteristics of modern material science, pushing the limits of performance while advancing circular economy and ecological stability for future outlooks.